with another proof. This time we are going to be trying to prove the theorem that says that if a quadrilateral is a rectangle, then the diagonals are congruent. We talked about that fact in class, but now we're going to prove it so that we can use it in future proofs, and so that we know that I wasn't lying to you, or your teacher wasn't lying to you when they told you. So the only thing we're given is that this ABCD over here is a rectangle, and we're being asked to prove that AC, this diagonal here, is congruent to BD, which is this diagonal here. We did give you a hint on this one, which says first prove that ADC is congruent to triangle BCD. I find that when I'm being asked to prove these triangles, especially when they overlap like this, it's helpful for me to draw a straight line and to highlight what I'm being asked to look at. So I want to look at ADC and I want to look at BCD. So if you can draw yourself a line there, then you can see the two triangles that we're looking at and kind of see that, okay, this is going to, if I can prove that these are congruent, then this is going to have a corresponding part here with this BD and with this AC. So that makes sense then that I want to look at these two triangles. All right, so let's, as per usual, start with what we're given. We're given that I have ABCD is a rectangle. The reason I know that is because given. All right, well, what does me knowing that it's a rectangle tell me? The definition of a rectangle is that a rectangle is a parallelogram that has 90-degree angles. So that means it's probably helpful to know that this rectangle is a parallelogram and that this angle ADC right here, this angle ADC is a right angle, and also angle BCD is a right angle. Okay, well, one of the first proofs that we did was that all right angles are congruent. So I can know that angle C and angle D, these two angles here, are congruent because of my right angle congruence theorem. Okay, so I've got some angles. Now, it'd be nice if I could say that this is congruent to this. Can I say that? Well, yeah, in one of the proofs that we just recently did, we proved that in parallelograms, opposite sides are congruent. Well, this is a parallelogram by definition. We already said that. So that means I can say that AD is congruent to BC. Notice that I'm marking it as I go because that's going to help me figure out what sort of congruence I have in the end. So AD is congruent to BC. I know that because opposite sides of a parallelogram are congruent. There's not a nice pretty theorem name for that. You just have to state this is fact. It's fact that we've proven. All right. Now, I have an angle and a side. I would like, let's see, I've got side angle. It'd be nice if I could do something with this. Well, duh, it's the same line. So I can definitely say that DC is congruent to CD because they're the same line, and that's that reflexive property of congruence. So if I go through and look at what I've got, I have an angle, I have a side, and I have a side. But if I mark it, what I actually have is, let's see, this is congruent to itself. So what I actually have is side, angle, side. So it's not in the nice pretty order here because we kind of talked about those right angles first, but you've got this purple side and then a right angle and then the red side, and on the other triangle you've got purple and then the right angle and then the side. So I can say that triangle ADC is congruent to triangle BCD, which is what the hint told me to prove, and the reason I know that is because of the side angle side. But how does that help me know that AC is congruent to BD? Because that's what I'm supposed to be proving. Well, if this side, AC, is going to be A and C, then it is corresponding to B and D. So, corresponding parts of congruent triangles are congruent, so now my proof is finished. I have proven that AC is congruent to BD. So now, in the future, anytime I have a rectangle, I can know that those diagonals are congruent. Hopefully that helped clear a little bit up for you and refresh your memory, and I'll see you in the next proof. Bye.